Hi, everyone. Welcome to this fifth lecture on practical introduction to quantum computing. I would like to start saying that we have solved the problems that we encountered in uploading the recordings of the sessions to YouTube. So now you can find on the CERN lectures channel both the third and the fourth lectures. Sorry about the inconvenience. Now we think we have solved all the technical problems, and hopefully the new recordings will be available much sooner. Okay. So I would like to start today by running a notebook that we didn't have time to run last week. So let me share my screen with the quantum IBM experience. Okay, so you should now be seeing my screen with the quantum IBM experience, and I'm going to this notebook, which is number 8. As always, you can find it on the Indico page for the lecture. And in this notebook, we are going to show how to run some algorithms that we already have programmed with a different technique. But now we are going to do this in a higher level way. So you have noticed that up to this moment, all the algorithms that we have implemented have been described at the circuit level. So we have first constructed the registers, the quantum registers, then we have applied several different quantum gates, and then we have applied our measurements. And this is a interesting way of taking a look at these algorithms, and this is something that you need to do to understand what is going on. But as you can imagine, this is similar to what you do when you learn a classical programming language. You start by programming very simple functions. For instance, I don't know, a function to compute the minimum of a list, or a function to compute the product of two matrices, or something like that, just to understand the algorithms and to learn the different instructions that you have in the programming language. But when you do programming, when you write an application, usually you don't write your code at such a low level. You use already implemented functions from different libraries, and you use that to speed up the process of writing your programs, and also to have more reliable and faster code. Okay, so of course this is something that we also do when we write programs in quantum computing, and each programming language for quantum computing has its own set of pre-programmed algorithms and circuits. In the case of IBM Qiskit, which is the framework that we are using, we have this module which is called Aqua, which implements several commonly used circuits and algorithms. Okay, and today we are going to start by learning how to use these algorithms in these two cases that we studied last week. So first, I'm going to start with the Deutsch-Jotze algorithm. And as always, I need to do some imports. You see here that now I'm including some functions, some procedures from Qiskit Aqua. Okay, and this is where we are going to have these algorithms and these circuits already programmed. And what this allows me to do is to define the oracles that we need for both the Deutsch-Jotze and the Grover algorithm at a higher level. Okay, so for instance, remember that for the Deutsch-Jotze algorithm, what we need is an oracle that implements a function, a Boolean function, that is either constant or balanced. Okay, so we can use to define this oracle, this already implemented function, which is called truth table oracle, that produces a circuit that implements a Boolean function whose values are given in this parameter here. And the values are given in lexicographical order. Okay, so here, for instance, I have a function of two variables. So we have four possible strings and then four possible outputs. And this is the output for input 0, 0. This is the output for input 0, 1. This is the output for input 1, 0. And this is the output for input 1, 1. Okay. And of course, this is a balance function. We are going to use first a balance function and then a constant function. And you can also draw the circuit that is produced by Aqua automatically, instead of you needing to see what are the gates that you need in order to implement this oracle. Okay. Then we also have an implementation of the Deutsch-Jozsa algorithm already in Aqua. Okay, and to instantiate this algorithm, we only need to provide the oracle on which we need to, or we want to use this Deutsch-Jozsa algorithm. Okay, so with these simple instructions, we can instantiate the Deutsch-Jozsa algorithm with the oracle that we have already defined, and we can see here the circuit that is produced by Aqua. Okay, and you see that this is exactly the same kind of circuit that we were using last week, but in that case, we were implementing all the different gates one by one. Okay, now to run this algorithm, of course, I could just simply take this circuit and run this circuit as we always do. But when we define, or when algorithms are defined in Aqua, they also provide some context for this execution. Remember that when we run this circuit in the Deutsch-Jozsa algorithm, then we measure the top qubits, and if they are 0, if they are all 0, we know that the function is constant. And if some of them, or at least one of them, is not 0, we know that this is a balanced function. Okay, so this is something that is also already programmed on the Deutsch-Jozsa algorithm. We don't need to take the output and compare it to the 0 string. This is something that is it's already done for us in the implementation. Okay, so here, if I run this, I obtain the measurement, which was, well, in this case, it was run 1024 times, and in all the cases, we obtain 0, 1, and the result, and this is the interesting thing, is that the function is balanced. So I don't need to remember what are the possible outputs. This is something that is already programmed. Something that is different when we use this implementation is that instead of taking the circuit and running it on a backend, we need to define what is called a quantum instance. This quantum instance, in this case, only depends on the backend that we want to use, but in general, it can have more parameters in its creation. We will talk about this later. But the idea is that we provide some backend encapsulated in this quantum instance to the algorithm, and the algorithm uses this quantum instance as many times as it needs, and it computes the outputs, and from these outputs, it gives some result, which in this case is whether the function is constant or balanced. Okay, so this is convenient because I just can forget about the details of the implementation. I can just provide the input and check the output for my particular case. Now I'm going to do the same, but with a constant function. A constant function in this case that always returns 0. Here we have a Boolean function which takes 3 variables as input. That is why I have here a string of length 8. 2 to the power 3 is 8. And then I see here that taking only the part of the result from the whole output that the Deutsch-Jozsa algorithm provides, I can check easily that this function is indeed constant. Okay. For Grover, we can do something similar. We can just define an oracle, which in this case, it's a function of 2 Boolean variables and returns 1 only on one of the inputs, okay? And then I construct the Grover algorithm with this oracle, and I also provide a number of iterations, okay? This is something that I can do in Grover. I can specify how many iterations I want to perform. Of course, in Deutsch-Jozsa, I only needed to provide the oracle, but here I can also provide this parameter. Remember that in this case, since exactly 1 out of 4 possible inputs returns 1, with just 1 iteration, we are going to measure with probability 1 the element that returns 1, the marked element. Okay, so if I run the algorithm, the Grover algorithm, with the quantum instance that I had prepared before for the Deutsch algorithm, I see here that the result again contains several different pieces of information, the result of all the measurements, what was the measurement that was more frequent. I can also obtain the circuit if I want to check it. This is the assignment, which is the variables that are set to 1 in the result of the execution. Since I'm having 1, 1, both the first bit and the second bit are set to 1, and the evaluation of the oracle on that element. In this case, it's true because it has found the element that was marked. Okay, so this is a convenient way of running this Grover algorithm without having to explicitly define the oracle and all the circuit and running it and checking everything. Okay. Another thing that I can do with these functions that are implemented in Aqua is to define the oracles in a more comfortable way, or a way which is more similar to how we write functions or logical expressions in regular logic, in classical logic. So for instance, here I can write this expression, which is the OR of X and Y, and the negation and Y or Z, and so on. And I can run I can define an oracle with this expression, and I can run the Grover algorithm, for instance, for 3 iterations. And again, I have here the different pieces of information that the execution of the algorithm returns. So now you see that we have measured several different elements, but the most frequent one is this string, and this string corresponds to, well, you need to notice here that the order in which the bits are given in Qiskit is the reverse of what we expect. So this is, for instance, the second qubit. That is why here it's -2. It corresponds to this bit being 0. And in this case, again, the oracle evaluation on this element that we have found is true. Okay. Another thing that is interesting with the implementation, the Grover implementation in Aqua, is that we can use this incremental mode that we studied last week. If you remember, a crucial part of the execution of the Grover algorithm is to determine the number of iterations that we want to use in order to find the element. But this depends on the number of elements that satisfy the condition, and this is something that maybe we do not know in advance. In that case, we can use several techniques. One of them is what we call the incremental search, and this is something that is implemented in Grover in Aqua, and we can use it instead of providing the number of iterations. The algorithm will start with 1 iteration and will increment this number of iterations until it finds an element. Okay, so in this case, if I run this, well, this is a little bit slower because it has to try different numbers of iterations, but after some time it will return the result, and in this case it finds that a possible element that satisfies this Boolean formula is this one, which sets every variable to true. And of course, this makes this expression true because I can, for instance, take this part here, this AND of the 4 bits, and this makes the formula true. Okay, so this is just a glimpse of what you can do with Aqua. I wanted to show you how to run 2 algorithms that we already studied, but we will use aqua a lot in all the different, in this lecture and the following lectures in all the different algorithms that we are going to study. Okay, so I don't know if there is any question about this. If not, let me please go back to my slides. And we are going to sorry. We are going to study a new algorithm that is Shor's algorithm, probably the most famous quantum algorithm out there. This was proposed by Peter Shor about 25 years ago. I think it was 1994, 1995, and it quickly became very famous because it allows us to find factors of big integers in an efficient way. Okay, and well, this is a problem that may seem not very important, not very relevant, until you remember that much of the current cryptography that we use for our transactions on the internet is based on this RSA crypto system, whose strength is based on the difficulty of factoring very large integers. Okay, so this is something that with a classical algorithm we do not know how to do efficiently, but with this algorithm proposed by Shor, we could do it if we had a big enough quantum computer in an efficient way. Okay, so here you have the expressions of the complexities of these algorithms. For the Shor algorithm, we have something that is polynomial. In fact, is a little bit bigger than n squared, where n is the number of digits or bits in the expression of the integer that we want to factor. Whereas the best classical algorithm that we have today has a complexity that grows almost exponentially with the number of bits. Okay, it's not completely exponential. It's like the order of an exponential of a root of the number of digits, but this is grows much bigger, much faster than any polynomial. Okay, so this becomes impractical very fast when we have, I don't know, several thousand bits in the expression of the integer that we want to factor, while this could still be doable with a quantum computer because the complexity in this case is polynomial. Okay, so this is an algorithm that it's very important. This made the study of quantum computing very interesting for the reason that, well, it can challenge our current cryptography methods, and it's something that attracted a lot of attention to the field of quantum computing. Okay, so we are going to study how to do this with this algorithm, how to factor integers with this algorithm. And in fact, it turns out that the algorithm is more or less simple. Okay, this is all the steps that we need to perform. You see that in just on a slide, I can state all the steps in the algorithm, and many of them are very simple. There is just one step that we need to do with a quantum computer. The rest of the steps we can do with a classical computer. And this is something that we are going to see more and more in the algorithms that we study. These are what we call hybrid algorithms, in which we have part of the process done in a classical computer and part of the process done in a quantum computer. Okay, so what are the steps in this Shor's algorithm? Okay, so we are given a number, this big N here, this is an integer, and we want to find at least one non-trivial factor of this number. So the first thing that we need to do is to check whether it is a prime or a power of a prime. Okay, this is something that we can do efficiently with classical computers, and if we find that the number is a prime or a power of a prime, we can stop there. Okay, this is like the easy case. If the number that we are given is not a prime or a power of a prime, then we choose at random a number a between 1 and n, strictly greater than 1 and strictly lower than n, okay? And then we compute the greatest common divisor of a and n, okay? If we are very, very lucky, then maybe this greatest common divisor is bigger than 1. This is this number b that I'm using here. If this b is greater than 1, it means that we have found a common factor. We have found a factor of n, and we can stop. But this will happen not very often, okay? So if this does not happen, if we are not lucky, we proceed to step number 4. Step number 4 is the one that we are going to do on the quantum computer. I will explain more about this later on, okay? But the idea here is that we want to find what we call the period of or order of a mod n, okay? That is a number r, which is bigger than 0, an integer number bigger than 0, such that a to the power r mod n is equal to 1. So when I divide a to the power r by n, the remainder that I obtain is 1, okay? So this number r will be very important in order to find the factors of the integer n, okay? So we find this. I will explain how to do this with a quantum computer. Of course, we could also do this with several different techniques in a classical computer, but we do not know of any efficient way to do this in a classical computer, and that is why we need to use here a quantum computer, because this is the part that we can do efficiently in a quantum computer. Okay, so imagine that now I have found this period or this order r. Now I check if it is odd. If it is odd, it is not good for what we need in the rest of the algorithm. So we go back to 2. It means we choose a different a, okay? Now, suppose that we have found this r and this r is even. Then we compute these numbers here. Since r is even, I can compute r divided by 2, and I can compute x and y as these reminders here, okay? Now I check whether x is 0 or y is 0. If x is 0, again, we are in a situation in which this value is not good for us, so we need to choose a different a. If y is 0, it means that a to the power r divided by 2 also verifies this condition here, okay? So we can try again with r divided by 2, okay? And see if that is even, and then we check again x and y, okay? Eventually, and this is something that you can prove, you need some statistical analysis for this. Eventually, you will find this a with an r that gives you x and y different from 0, okay? If you want the details of the statistical analysis, you can check, for instance, John Watrow's lecture notes that I have included in the recommended resources. And there you have an explanation of how to do this analysis, okay? So eventually we will find this a with this order r, and we have x and y, which are both different from 0. Now what we do is to compute p and q as the GCD of x and m and the GCD of y and m. And one of them, either p or q, it's going to be the non-trivial factor of n that we were looking for, okay? So why does this this work? Why p and q or q must be a non-trivial factor of n? Well, this is quite easy to see. First, notice that we are imposing here that x and y are different from 0, okay? So here it means that x and y are not multiples of n, Okay, this is what means the x and y having a remainder different from 0 when we divide by n. Okay, so the worst case that we could have is that P and Q are both 1, because if the x is not a multiple of n and y is not a multiple of n, then for this to be a trivial factor, P and Q should be 1. But this is something that cannot happen, because we know that a to the power r is congruent with 1 mod n, but a to the power r is the same as x times y mod r, because we have chosen x and y to be these two expressions here. Okay, and we know that this is 0, so it is not possible that both x and y are prime with relative prime to n. It cannot be that both P and Q are 1, because then we do not have this equality here. Okay, this means that x times y is a multiple of n, and then at least P or Q is a non-trivial factor of n. Okay, and as I mentioned before, it can be proved that we will reach the last step in which we compute P and Q with high probability. Okay, with a probability that is above a certain threshold, and if we repeat the method several different times, we will eventually find one of these factors. Okay, so this is an algorithm that will give us this factor of the big integer n, and in fact this was an algorithm that was already known before the invention of Shor's algorithm. But the problem, as I mentioned, was that this step 4 was not possible to do to compute efficiently in a classical computer. So the idea here is to do the rest of the steps in a classical computer. We can check, we have algorithms to efficiently check whether a number is a prime. We have algorithms, of course, to compute the GCD of two numbers efficiently, for instance, the famous Euclid's algorithm. We can do the rest of the computations in a classical computer, but step 4 is something that we will do in the quantum computer. And to do that, we are going to use this circuit here, which has a number of gates that is polynomial on the number of bits of the number the integer we are going to factor, and that is why this is efficient in the quantum computer. Okay, so what is this circuit that we have here, and how does it help in computing this period, this order of the number a? Okay, so we have reached step 4. So we have selected this number a at random, and we want to find r, its order. Okay, what we do is prepare this circuit here, in which in the top qubits we have first an initial uniform superposition. This is something that we already know how to do with Hadamard gates, and here we have the string that represents number 1 in a binary way. Okay, and then controlled by these qubits here, we perform an operation which is the power of a to this exponent here with increasing exponent mod n. Okay, this is something that is just a classical computation, and we know that any efficient classical computation is something that we can do with a quantum circuit also efficient. Okay, what we get with these operations here is to compute the values a to a power x mod n. Okay, and I will show you in the next slide what this gives us and why this is helpful for our task. Then we measure here, and we will obtain, we will collapse part of the state, and then we compute here something that we call the quantum, or the inverse of the quantum Fourier transform. And I will talk more about this later, okay? But I wanted to show you what the circuit looked like and what are the different parts in this circuit, okay? And now I'm going to explain why each of the parts does a helpful computation for this finding of the period and how it works in detail. Okay, so let's focus first on the first part. As I've mentioned, the column of Hadamard gates allows us to compute this uniform superposition here, this sum over all possible values of x, and then for a given value of x here, this unitary transformations, controlled unitary transformations, allow us to compute this value here, a to the power x mod n. Okay, this is similar to what is called the Russian multiplication or the Russian exponentiation, okay, in which we divide the exponent in its binary expression, and then we compute the different parts of the exponentiation. Okay, so with this we obtain this expression here, and what we have is each value x with its evaluation of a to the power x mod n. Okay, and remember that we want to find some x here such that this value is 1. Okay, because then we would have the period. Okay, this is what we are looking for. So what we are going to do is to measure the bottom qubits. Notice that we here measure the bottom qubits, and then this collapses to a superposition in which now this second part of the state is a concrete value C, which we cannot choose. If we could choose this to be 1, that would be perfect, but we cannot do that. We are going to obtain at random some value C. Okay, but this is surprisingly helpful. Why? Let's see what happens with an example. I'm going to choose here a equal to 2, n equal to 5, and m, which is the number of qubits that I use here for this evaluation, equal to 4. Okay, of course I know that n is 5 is a prime number. Okay, so this is a case in which I wouldn't be using Shor's algorithm, but to see a concrete example of how the algorithm works, it's helpful. Of course, this is not going to factor 5 because 5 is already a prime number. Okay, so what we construct with the first part of the circuit before we measure, it's something like this. This is 0, 1, 2, 3, the equal superposition, and each value it's entangled with the evaluation of the modular exponentiation. Okay, so 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, which mod 5 is 3. Okay, and 2 to the power 4 is 16, which mod 5 is 1. Okay, so this is the period. In fact, this is the period that we would like to find, but we cannot choose to select this value at will, as we discussed last week. Okay, so now we measure this, and this is going to collapse. We measure this part here, this part of the state, and this is going to collapse for some value. Okay, for instance, imagine that it collapses for 2. Notice that here for 5, I will have 2 entangled with 5 again. Okay, so I'm going to have now a superposition of all the values here that as the result of the modular exponentiation give me 2. Okay, and why is this useful? Because here I have 1, 5, 9, 13. The difference between one number and the next one is exactly 4, which is the period of the value 2. This is what I'm trying to find. Okay, so whatever the value that I obtain when I measure this second part of the register, here I'm going to have values which are exactly r units apart. And this is something that I want to find. I want to find the difference between these two, between one element and the next, okay? In order to do that, I need to use the quantum Fourier transform, or the inverse of the quantum Fourier transform. Why this quantum Fourier transform is useful? Well, this quantum Fourier transform, I will define it in the next slide, is the quantum counterpart of the famous discrete Fourier transform. And it has some very useful properties that are going to help us in finding this period. Well, the first property that is important is that it is shift invariant. It means that, well, here I can obtain 1 with 2, 5 with 2, 9 with 2, but I could have obtained 3 with 3, 7 with 3, and so on, okay? I'm going to obtain several different states, which are all of them separated by the same amount, but they can be shifted one from the other, okay? So this is something that for the inverse quantum Fourier transform is not important, okay? This is going to result only in a phase in the state that I obtain, and when I measure the state, remember that the global phases are not important. So this shift invariance, it's interesting because it allows me to treat all the different sequences that I can obtain in the same way, because they are going to give me exactly the same probabilities, okay? And the other property that is interesting is that this quantum Fourier transform moves the period, here we have a periodic sequence, moves this period R, or move these sequences of period R to sequences of period M over R. Okay, so this is something that you can see here in this graph. In this function, we have a period of R, and now after we compute the quantum Fourier transform, we have a period of M over R. Okay, so these are properties that you can check. I'm not going to check them. You can, for instance, refer to some of the books in the recommended list to check these properties, but I'm going to use a different way of showing why this Shor algorithm works, okay? So for that, I need to see what is this quantum Fourier transform, how it is defined, and what is the circuit that we need to use in order to compute it, okay? So the definition of the quantum Fourier transform for a basis state J is this expression here, this superposition here, that if you know about the discrete Fourier transform, you will see that it's very, very similar to the definition of the classical discrete Fourier transform, okay? The way in which we can compute this superposition is by this circuit here, in which everything is something that we already know from our previous study of quantum gates. We have, for instance, Hadamard gates, and then we have these controlled rotations, which are rotations over the Z axis, okay, with a given angle, okay? And then we have these swap operations between the uppermost qubit and the bottom qubit, and then the next ones. And this is something that we know we can do the swap operations, for instance, with CNOTs, okay? So this is the definition of the quantum Fourier transform. And the interesting thing here is that this is the counterpart, the quantum counterpart of the classical discrete Fourier transform. And here we have a polynomial number of gates. We have a number of gates that is quadratic in the number of qubits that we are using here. Okay, while in the classical case, for instance, with the famous fast Fourier transform algorithm, in order to compute this kind of transformation, we need an exponential number of evaluations. Okay, so here is where we have this advantage over the classical case. Okay, so with this definition, you could go back and study these properties and check that, in fact, you obtain this shift invariance and you transform periodic sequences of period R into periodic sequences of period M over R, or you can study this as a transformation from the time domain into the frequency domain. There are several different options to do this, but the one that I think it's more interesting in the quantum setting or in the quantum computing context is to see this algorithm as a particular case of something that is called the quantum phase estimation algorithm. Okay, so here in this algorithm we are given a certain unitary operation, and one of these of the eigenvectors of this unitary operation. Remember that a unitary operation is something that we can see as a matrix multiplication, and since it is unitary, it always has eigenvectors whose eigenvalues are of this form. Okay, the eigenvalues are going to be of the form e to the power 2 pi I, and then an angle which is between, or a value which is between 0 and 1. Okay, and the goal of this quantum phase estimation algorithm is, given this unitary U and this one of these eigenvectors, to estimate the value theta here, this value between 0 and 1. And this is something that we can do with this circuit here, which you can see it's very, very similar to the circuit that we have for the Shor's algorithm. And in fact, I will show that Shor's algorithm is a particular case of the quantum phase estimation algorithm. Okay, so why does this quantum phase estimation algorithm work? It works sorry. It works because what we are doing here in this first part is more or less the same that we were doing in Shor's algorithm. And after this part, what we have here is this superposition in which we have applied the operator on the eigenvector several different times, depending, a power of this unitary operator depending on this value k here. So we are going to obtain a phase that depends on this value k here. But if you check this expression against the expression of the quantum Fourier transform, you will see that it's almost the same. So if we try to identify the coefficients here, the phases here, you will see that we need the theta value to be k over 2 divided by m. Well, in this case, I have changed n and m, but it's the same. So if I apply now the inverse of the quantum Fourier transform, with the quantum Fourier transform, I go from J to this expression. And if I now have this expression, which is very similar to the result of a quantum Fourier transform, and I apply the inverse, I will go to something that is very similar to this value J. And the value J that makes this approximately equal to this expression here is exactly 2n multiplied by theta. Okay, if we identify the different elements in the two expressions. Okay, so this is something that we can do in order to obtain this value or a value that is close to these two to the power n theta. And this is something that now we can use in order to obtain the period that we were looking for in the case of Shor's algorithm, because it can be shown. This is something that you can find, for instance, in John Watrow's lectures, that the eigenvalues of the unitary operation that we are doing here, which is this exponential, modular exponentiation, are of this form, are exactly of this form, are exactly the period that we are trying to find. Okay, so this period that we are trying to find, it's encoded somehow, it's implicit somehow on the eigenvalues of this operation of modular exponentiation. Okay, so if we use this quantum phase estimation algorithm, which is what we are doing here with Shor's algorithm, we can recover this value R. Okay. For that, of course, if we apply the quantum phase estimation algorithm as we have explained, we would need at least to know one of these eigenvectors of the operation. And this is something that is in general not easy to do, because these eigenvectors depend on R, and R is what we are trying to find. But we can rely on the fact that the value that we are using at the beginning of Shor's algorithm is an equal superposition of all these possible eigenvectors of the operation of modular exponentiation. Okay, so by linearity, when we apply this, when we measure, we are going to collapse on the application or on the combination of the application of the quantum phase estimation algorithm with all the different eigenvalues that we have here. And when we measure, we are going to obtain an estimation of one of these values k over r. Okay, and this is exactly what we need, because from this now with some classical techniques using continuous fraction expansions and things like that, we can recover this value r, which is what we are interested in. Okay, so this is how Shor's algorithm works. There are a lot of details that I have not explained, but I refer you to John Watrow's lectures. Everything is explained in a lot of detail there, but the ideas are the ones that I have been discussing. This quantum phase estimation algorithm is also interesting because we can use it in other situations. For instance, remember that in Grover's algorithm, one of the key steps in the application of the method was to decide the number of iterations that we want to do. Okay, and this depends on the number of marked elements, on the number of elements that satisfy the condition that we are interested in. Okay, and this is something that in general we do not know. So what can we do? Well, we can use this incremental method that I showed, for instance, in Aqua at the beginning of the lecture, but we can also use Grover's algorithm together with the quantum phase estimation in order to obtain an approximation of the value of the number of marked elements, and then to use this approximation in the number of iterations that we use with Grover. For that, we need to notice that Grover's operator is of course a unitary transformation, and its eigenvalues are of this form where this theta is related to the number of marked elements by this expression here. This is something that you might remember from last lecture. This was exactly the angle of rotation that we were considering. Okay, so if we are able to estimate theta, then we are also able, with the quantum phase estimation algorithm, then we are also able to estimate k, and this is an approximation of the number of marked elements. Okay, there are many other algorithms in which this quantum phase estimation is used. I only want to mention very briefly this algorithm, which is called HHL, which was proposed by Harrow, Hasidim, and Lloyd in 2009, and can be used under certain conditions. I'm not going to detail everything here because it's a little bit complicated, but it can be used under certain conditions to obtain solutions of linear systems of equations. And this is something that I'm not going to explain. This algorithm is a little bit more difficult. With the ideas that we have been discussing, you can check more detailed treatments of the algorithm and probably understand almost everything. But it is relevant to us because this algorithm is sometimes used in other contexts, for instance, in quantum machine learning, something that we will be talking about in the next lecture. Okay, but the idea here is that Shor's algorithm is a particular case of quantum phase estimation, and this quantum phase estimation is a very powerful primitive that we can use in other contexts to speed up computations in other quantum algorithms. Okay, I don't know if there is any question up to this point. If not, what I'm going to do is to show you how to visualize all these periodic sequences that we are talking about in Shor's algorithm with Quirk. Okay, so I'm going to, you have here several different links. I have already opened one of these links in my browser, and I'm going to go to that screen, and I'm going to show you how to use, or how to visualize this algorithm with Quirk. Okay, so here the notation is a little bit different. What we called A here is called B. What we call M here is called R. Okay, but it's more or less the same. And this is the value X that we were talking about. Okay, so here what is done is this is a compressed expression of all these modular exponentiation that we had, and then we have the inverse of the quantum Fourier transform. And here I have included a visualization of what is happening just before we measure, before we apply the inverse of the quantum Fourier transform. And you see here that we have several different peaks that correspond exactly to the different values that we were seeing in that expression, in which we had each value with its the result of its modular exponentiation. Okay, here the bits are in the reverse order. So the first bits that you see here, these 0, 0, 0, 1, are the last part that we had in the slide, and the 0, 0, 0 is the other part. So this is 0 is B, which is 2 to the power 0, that gives 1. Okay, and you see here that we have different values, different states. All of them are associated to the power, to the modular result, to the to the result of the modular exponentiation, which is 1, and they are all grouped here, and they are all exactly 2 units apart. Sorry, 4 units apart. Okay, so you see here 0, 0, 0, 0 in the last part of the register. Here you see 0, 1, 0, 0. The next one is 1, 0, 0, 0. This is 8. The next one is 12. Okay, so this is exactly the separation in 4 units, which is the period. Okay, and for the other results of the modular exponentiation, these are 2, these are 4, and this is 8. Because now we are taking the mod as 15, we obtain exactly elements which are 4 units apart. And this is what we recover with the inverse of the quantum Fourier transform. Here you see that the possible results are 0, 4, 8, and 12, okay? Which is the result of multiplying 2 to the power 4, which is the number of qubits that we are using here, times a fraction which has in the denominator the period 4 that we have here. Okay, so this is exactly what we were seeing in the case of in the slides, but now in a graphical way. If I change here the value, this is something that you have in the links that I have used in the slide. For instance, if I change this to 4, now I have different values because the period of 4, instead of being 4, like in the case of 2, it's 2. Okay, and this changes the nature of these sequences, but they are all, again, all that these are clustered together, they are 2 units apart. If I use, for instance, here 14, I obtain something similar. Again, the period of 14 mod 15 is 2. So I obtain elements which are 2 units apart. And here I can measure either 0 or 8. Okay. This is something that you want to remember for the application that we are going to do in the notebook with Qiskit, notice that for 14 and for 4, we obtain exactly the same possibilities here, okay? Because both of them have period, which is 2, okay? There is also another link in the slide, which is for the case that is already implemented as an example here in Quirk, which is the case in which we have A or N, in this case, the number that we want to factor equal to 55, and the value that we call A equal to 26, okay? And in this case, you see that now we don't have these peaks, which are just isolated possibilities for measurement, okay? This was the case in the examples that I showed before, because the periods were powers of 2, and in that case all that we obtain is always exact. But when the period is not exactly a power of 2, we can have these peaks here that gives us the correct period that we want, but then we also have some approximate values around these peaks, okay? That is why we have, I don't know if I can make it a little bit bigger so you can see, we have a peak here, but we have surrounding this some other values that we can obtain with lower probability when we measure, okay? So this is something that we also need to take into account when we apply Shor's algorithm. The easiest analysis is when the period is a power of 2, but we can have other situations, and then we need to do some further analysis, but everything works out in the end, okay? So these are the cases that you can have, and this is the way you can see this with Quirk, okay? Now I'm going to show you how to run this with Qiskit, okay? So let me go back to this, to my browser with the IBM Quantum Experience, and here I have prepared this notebook with Shor's algorithm implemented in Aqua, okay? So again, this is something that we do not need to specify on at the level of circuits. Of course, you can implement everything with the gates that we have studied, and you can produce your own circuit, but you don't need to do this because this is already implemented in Qiskit. Of course, you can go and check the source code. Qiskit is free software, so you can check the source code and see how it is done. But the idea is the one that I have been explaining in the slides, okay? So here, to execute Shor's algorithm, I only need to provide the value that I want to factor, and then the value A that I want to use in order to obtain the period of A, and then estimate the factor. So here, for instance, I'm using 15, and the probe is 2, okay? And after some executions of the circuits that we have been discussing, this quantum phase estimation with the modular exponentiation, the result that I obtain is these factors 3 and 5, okay? Now what I'm going to do is to do this for different values of A, okay? And the first thing that I do is to check whether N and A already have some common factors. And if they don't have common factors, I'm going to run Shor's algorithm, okay? So here, for instance, this is the same case that we had already run. Here, 3 is a factor of 15, so I don't need to run Shor's algorithm. Here, for the value of A equal to 4, I obtain again the factors, and well, several other different cases, okay? You can check each of them. What I want you to think about is why, in this case, when A is equal to 14, I obtain nothing, okay? In this case, Shor's algorithm was not able to find the factors, okay? And I want you to remember that in Quirk, we showed that the period of 14 and the period of 4 was exactly the same, was 2. So this is a question for you, and simple exercise. You just need to check the definition, the steps of the algorithm, and see why in this case we are able to find the factors and why in this case we are not able to find the factors. Okay, this is also interesting because you can see here that for some values of A, we are not going to be able to obtain the result that we expect. Okay, but in the algorithm, this is something that we had already considered, and then we go back to step 2 and select a different value of A, and then try again. And with the statistical analysis, we see that this is something that will not happen very often, and eventually we will obtain these factors that we are looking for. Okay? Any question up to this point? Okay, let me go back to my slides. Okay, there is this question by Bogdan Vulpescu, which is, in results, what is total counts and successful counts? I'm not sure how this is implemented at the low level in Qiskit, but I think that total counts is the total number of executions of the circuit, and successful counts should be the number of times that a period was correctly identified. This is something that I can check for you, but I suspect that this is what is being done here. Okay, so I will take a look at the concrete implementation in Qiskit, and I think it will be something like that. Okay, I will check and I will confirm next week. Okay, any other question? Okay, so up to this point, we have been studying algorithms which somehow require that our quantum computers are perfect. They perform all these operations perfectly, they measure all the results perfectly, and we do all our analysis taking as a given that we are able to implement all this perfectly. Okay, but this is something that is not realistic in the current situation with the quantum hardware that we have. We already have seen several situations in which the execution on the actual quantum devices gives us some errors. Okay, so in the last decade or so, or maybe a little more, several different algorithms have been proposed to use these quantum computers that we have now, which are sometimes noisy, which are of small scale, have not a lot of qubits, in order to implement something that is useful. Okay, that is useful now and that can solve some interesting tasks now. Okay, so I'm going to turn now my attention to these algorithms which can be implemented with the computers that we have today, and we are going to study several different algorithms that we can use on this lecture for quantum for the problems of combinatorial optimization, and in the next lecture for quantum machine learning. Okay, so now we are going to turn our attention to this combinatorial optimization problem, starting with a problem that is stated when we are given a certain graph. So we have these vertices and they are connected by edges, and we are asked to divide the vertices of this graph into two different groups. Here we have used white color for one group and black color for the other group. Okay, and the goal of this division into two groups is to do it in such a way that we obtain a lot of edges which have extremes in groups of different colors, okay? This is what we call a cut. We say that one of these edges is cut when it has extremes. The vertices it connects are in different groups, okay? And what we are considering is what we call the maximum cut problem. So we need to divide the vertices into two groups so that the number of edges with extremes in two different groups is the maximum possible, okay? So this may seem a not very interesting problem, something that it's almost a game, okay? But it turns out that this problem is surprisingly difficult and also surprisingly useful, because this is a problem that can be shown to be NP hard. So any other problem that is in the class NP can be reduced, can be transformed into an instance of this problem. And we do not know how to solve this kind of problem with a polynomial algorithm, with a classical polynomial algorithm, okay? So this is a combinatorial optimization problem, because we need to select among these 2 to the n possibilities what is the one that gives us the best possible value in the number of edges that are cut. And this is a problem that is difficult to solve, but if we knew how to solve this, we could solve other different important problems, okay? This is also a problem that is what is called APX hard. I'm not going to give the complete definition or the formal definition of these kind of problems, but the idea is that it is also very difficult to approximate the solution to do this problem, okay? We cannot approximate the solution to a precision as good as we want with a polynomial algorithm, unless P is equal to NP, which, as you know, is something that we consider very, 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 very unlikely. Okay, so this is an instance of a very difficult problem, and this is a problem that we are going to show that we can approximate or try to solve with quantum computers in a quite natural way. Okay, so how to do that? The first thing that we need to do in order to transform this into an instance of something that we can approach with a quantum computer is to identify the group that we are assigning to each of the vertices with a variable set that is assigned to each of the vertices I. So set I is the group that is assigned to vertex I in the graph, okay? And we are going to give -1 to one of the groups and 1 to other group. For instance, 1 is white and -1 is black, okay? It doesn't matter. So now we see that the problem of finding this maximum cut is equivalent to minimizing this sum of products of this variable set that we have here, where the products are taken over the edges, okay? So if we have an edge that connects vertex I with vertex J, we add one of these terms in this sum, okay? Why is this equivalent? Why minimizing this is equivalent to solving the maximum cut problem? Because if you notice the different possibilities that we have here, if set Y and set J are in different groups, one of them is going to be 1 and the other one is going to be -1, and the product is -1. So this makes the sum go lower, okay? But if both are in the same group, then they are both 1 or both -1, and then we add 1, so we are making this sum bigger, okay? So if we can make this sum the minimum possible, then we are making all these edges have extremes in different, or most of these edges have extremes in different groups, okay? So this is the relationship of this formulation, which is a purely algebraic or combinatorial formulation, with this formulation in terms of graphs, okay? And now we can transform this problem into something that we can approach with quantum computers. The selection of the value or the name set here was not casual, okay? Because this is related to the set operator that we have already studied, okay? I'm going to explain how to do that, but first, a simple example that we are going to use in order to study this transformation from this combinatorial problem into something that we can solve with quantum computers. So here we have this simple graph with 3 vertices, and then here the problem is to minimize, it's equivalent to minimize this value here, okay? Because 1 is connected to 2, so we have this term here. 1 is connected to 3, so we have this term here. Of course, this problem is very easy because you see that we just need to cut the graph here to put 1 in one of the groups and 2 and 3 on the other, and then we have the maximum cut, okay? You also can enumerate all the different possibilities, the 8 possibilities, and then you see that we can identify these two different cuts or groups that we can make with the possibility 0, 1, 1 or 1, 0, 0, where this means that we are putting 0, we are putting 1 in group 0, we are putting 2 and 3 in group 1, or we are putting 1 in group 1 and 2 and 3 in group 0, which is the same, okay? So these strings here somehow codify the solution or one of the solutions to this problem, okay? Now we can transform this into something that we can approach with a quantum computer by taking into account that, well, this can be the state of qubit register, and we can use this as the operators, the set operators that we have been studying in our quantum circuits, okay? So remember that the expression as a gate of the set operator is this matrix here, okay? And that vector or the qubit in state 0 can be represented by this column vector. Then if I compute this multiplication here, matrix times this vector or column vector, and then times this row vector, it is easy to see that I obtain 1, okay? And we can denote this in a different way, which is what we call Dirac notation. We have used this several different times in this way here. So this is matrix set, and this is the expression of the state 0 as a column vector. This is the expression of the vector 0 as a row vector, okay? What we call the bra and the ket, okay? So we can do this when we have 0. We can do this also when we have 1. When we have 1, this is the expression for the state as a column vector. And if I do the same computation, I obtain -1, okay? Why do I do this? Because you see that from the state of a qubit, I can obtain, and this sets, I can obtain the 1 or -1, which is the value of the variable corresponding to that assignment of the vertex, okay? If I assign a vertex to group 0, then when I evaluate over set, I obtain 1. When I assign a vertex to group 1, I obtain -1. So I'm obtaining these values of the set variables that I wanted in order to compute this summation and to try to minimize that, okay? Also, if we have more qubits, we can compute these products, this matrix surrounded by this column vector and this row vector, by taking into account that this is in fact a tensor product, okay? This is a tensor product of matrices, and it's easy to check that then we can just compute each of the different products of these sets times the states of the qubits independently, and then multiplying the results, okay? So for instance, in this case, since we have a 0, we are going to obtain 1. In this case, since we have a 1, we are going to obtain -1, okay? And the value, the total value of this product here is -1, which is the same as the value that we obtain when we assign vertex 1 to group 0 and vertex 2 to group 1. Okay, so this is a way of obtaining this value for this term here as something that comes from the values of the qubits that we are going to use to represent the assignment of vertices to groups. Okay, also for the other part of this expression here, we can do the same computation. Now I'm using the 3 qubits, all the 3 qubits, and notice that since I don't have a set 2 here, I don't need to use this value here, okay, which is the assignment of the, or the state of the second vertex, okay, and then I compute each of these products independently. Each of them is going to give me -1, and then the result is going to be 1. Okay, so this means that if I have this assignment and I want to evaluate the value under this assignment of this term here, I can just compute this product. Okay, and by linearity, of course, if I have the whole expression, what I can do is to evaluate one assignment, for instance, this one here, multiplying the whole matrix H here with the column vector and with the row vector. And in the end, you can check this computation is very easy. You obtain here, for instance, that the result is -2, okay? Because here I have 1 in one group and 2 and 3 on the other, okay? So this is going to be -1, and this is also going to be -1, okay? But if, for instance, I take this assignment here, in which 1 and 3 are in the same group and 2 is in a different group, I see that for the first term, I obtain that 1 and 2 are in different groups, so I obtain this -1, and 1 and 3 are in the same group, so I obtain 1. So this value is 0, which is not the minimum possible. Okay, this is something that we already knew without having to do all these computations, but this is going to help us for more complicated cases in which we have many different vertices. Okay, what happens here? We have transformed this problem of minimizing this expression, giving values 1 and -1 to these variables, to a problem of obtaining a basis state, a state of a series of qubits, which makes this product here, this value here, the minimum possible. Okay, this is something that the physicists know very well. Okay, in fact, this matrix here is what we call a Hamiltonian. This is a Hermitian matrix. And what we are doing here is to computing this value, which is sometimes called the expected energy or expected value of the state with this Hamiltonian. And we are trying to find a state that has the minimum possible value of this energy, of this expected value for the Hamiltonian. This is sometimes called, or is often called, finding the ground state of the Hamiltonian, and this is a central problem in physics. Okay, so here we have a connection to the possibility of using physical processes in order to solve this kind of problem, and this is what we are going to do. Okay, we are going to do this in a particular case, which is also very famous, which is called the Ising model. In the Ising model, we have a generalization of this kind of expression that we had here for the Hamiltonian, in which now we have several different terms that can have coefficients which are real numbers, which involve the product of the set operator on two different elements y and I and j. And we also have this other term, which only involves the value of the operator on one of the terms, okay? This can be related to a problem in which we have several different particles with a spin, and these spins can be up or down, which corresponds to the values 1 and -1. And this Hamiltonian here expresses the interactions between the different particles. And what we want to find is a configuration of these spins, of these orientations of these ones and -1s that makes the total energy with respect to this Hamiltonian the minimum possible. This is again a problem that is NP hard, because as a particular case, it includes the max cut problem. If we set these values all to 0 and we set these values to 1 when we have the vertices connected in the graph, okay? And this is a problem that is has been studied in physics a lot, okay? And this is a problem that at the same time is connected to this combinatorial optimization situation that we are discussing, okay? A different formulation of these combinatorial problems related to this Ising model is what we call the QUBO, the quadratic and constrained binary optimization, in which we substitute the values set here, which can take values 1 and -1, with variables that can take values 0 and 1, okay? And then with these transformations here, which goes from the 1 -1 domain to the 0 1 domain and back, we can transform this matrix here into a matrix or an optimization of an expression of this form. Okay, so this is something that you will usually see also connected to these problems of combinatorial optimization with quantum computers. And I wanted to show you what is the relationship between the Ising model, which is the one that we are going to use, with this QUBO formulation. Okay. So imagine now that we have our combinatorial optimization problem. We have expressed it as the minimization of this Hamiltonian for an Ising model, and we want to solve it. We want to find the ground state. How can we do that? Well, we can use the fact that this is in fact a physical process. This Hamiltonian here is expressing the different interactions and the different forces that are acting on these particles that we have here. So we can try to build some device that mimics this evolution, this dynamics of this Ising model. Okay, and this is what we do when we consider what we call adiabatic quantum computing. The idea behind this adiabatic quantum computing is that there is this adiabatic theorem that roughly says, this is not the mathematical formulation, but roughly says that if we have a system which is in the ground state of a given Hamiltonian, we know that it is in the minimum energy state, and then we apply a Hamiltonian which acts slowly on this state. And this Hamiltonian is a time-dependent Hamiltonian that changes over time. If we apply this Hamiltonian for a slow enough evolution time, what we obtain at the end is a new state of the system, which is again in the ground state of the final Hamiltonian, okay? So the idea here is that if we do not inject energy to the system, it is not going to be able to jump from a ground state, a state of minimum energy, to an excited state, and a state which is more energetic than the ground state, okay? And we are going to apply this, in our case, with a Hamiltonian that is time dependent, and it's going to be defined from an initial Hamiltonian and a final Hamiltonian that encodes the problem that we want to solve. So imagine, for instance, that I want to solve the Ising model, or I want to solve a certain instance of the max cut problem, okay? So my final Hamiltonian will be that instance of the problem I want to solve. And the initial Hamiltonian, it's going to be a Hamiltonian, a simple Hamiltonian for a situation in which I know, or I can prepare easily, a state that is in the ground state of this. It has the minimum energy related to relative to this Hamiltonian, okay? And what I'm going to do is to apply a Hamiltonian that slowly changes from the initial Hamiltonian to the final Hamiltonian, which encodes the problem that I'm interested in. So varying this value t from 0 to this t, this big T, capital T, you see that when t is 0, this is 0. So we only have the initial Hamiltonian. And when I get to t equal to this big T, then this goes down to 0, and I only have the final Hamiltonian. So what I'm doing here is to start in an initial state that I can prepare, that is easy because physically I can prepare that with my device. And then I'm going to slowly change the Hamiltonian, so the system begins evolving according to this Hamiltonian, until at the end I have only an action that is given by the Hamiltonian that describes my problem. And if I do this slowly enough, since I have started in a ground state, I'm going to end also in a ground state. And this ground state is a solution to my problem, because now the Hamiltonian is the one that encodes my problem. Okay, so this is something that we can study as a model of computation, and in fact it's equivalent. It can be shown that is equivalent to the usual quantum circuit model that we have been studying. Okay, but again, it's difficult to implement in practice, because you need to be able to implement these different Hamiltonians, which can be physically challenging in some situations. Okay, so how can we use this in practice, or how is this used in practice? In practice, we use something that is called quantum annealing. In quantum annealing, which is the basis of the D-Waves quantum computers that we are going to use now, we are going to register on D-Waves Leap platform, and we are going to try to solve some problems using these quantum computers. So the idea is that these quantum computers implement this kind of time-dependent Hamiltonian, where this final Hamiltonian is not every or any Hamiltonian that I could be interested in, but only an Ising model Hamiltonian, okay, which is interesting in itself, because we know that this allows us to encode interesting problems like the mass cut problem or several different NP-hard problems, okay? And also a difficulty that we have with this adiabatic model is that, of course, in order to satisfy the conditions of the theorem, the evolution has to be very slow, has to be slow enough. And if you study this adiabatic theorem, you will see that, in fact, the time of the evolution, the time it takes the initial Hamiltonian to transform into the final Hamiltonian, must grow as the inverse of the square of the difference between the minimum energy and the next excited energy over all the process. Okay, so the energies of the Hamiltonian, depending on t, if sometimes are very close, this is going to give me a very small gap. And if I go very fast with evolution at that moment, I can risk jumping from a ground state to a excited state. So I need to do this. I need to do this slowly enough. Okay. The problem is that now we have transformed the computation that we wanted to do in the beginning, which was to find the minimum eigenvalue of this Hamiltonian, of this matrix, to computing many more eigenvalues, because in order to compute this spectral gap, I need to solve or to find the ground states and the next excited state for all the values of t here. Okay, so this problem is even more complicated than the one that we had before. So what do we do in practice? In practice, it's not easy in general to compute this spectral gap, this difference, and then to determine the time that I need to do this evolution. So in practice, what we do is to use what is called quantum annealing, okay? We take a simple Hamiltonian, which is this one here, whose ground state you can check that is this superposition that we know how to prepare, because we only need to use, for instance, Hadamard gates. And then, as I mentioned, the final Hamiltonian is not any Hamiltonian, but an Ising Hamiltonian, okay? And about the time t, we do not care about trying to compute the real time that we need for the whole process to be adiabatic. We just try with different values of t. We measure our solution at the end, our state at the end, and we check what is the value that we obtain. And hopefully that will give us a good approximation of the solution to the problem that we are considering. This has been tried with many different situations in practice, and is something that we cannot prove that always gives a good solution or always gives the best solution, but it can be useful in some situations in practice. For instance, this has been used, I will go back to this slide to show you the examples in a minute, but this has been used in high energy physics, okay? In these algorithms that we are studying today and next week, as I mentioned, we can use them with actual quantum computers. So I'm trying to show you for each of them at least one situation in which they have been applied to problems in high energy physics, okay? So here I'm highlighting this work by researchers from the University of Southern California and also from Caltech, in which they use this quantum annealing for a problem in which we have events that come from particle collisions, in which two gluons are involved, and we also have the production of two photons. And we have one interesting kind of events in which a Higgs boson is produced and then decays into these two photons. And we want to separate this signal, this interesting type of events, from other more conventional events, which are the background. Here I'm showing two. If you check the paper, there are several other background events in which there is no production of the Higgs boson, but you have also the gluons and also the photons. Okay, so this is in fact a machine learning problem, a classification task. So what did these researchers do? Well, what they did was first to collect some information about these events. They considered 36 different variables, and which each of these variables, they, independently of the results or the values of the other variables, they constructed what they call a weak classifier, a classifier that only takes into account the value of that variable and classifies the event into signal or background, depending only on some computation that they perform with that variable, okay? So these are classifiers that are not very good because they do not take into account all the information. So what they consider, these are the classifiers that are called here C sub I. So this gives a value of 1 or -1, depending on whether it is background or signal, okay? And what they did was to consider a combination in a strong classifier, which is a linear combination with these coefficients W sub I, which can be 0 or 1. You can consider the output of the weak classifier or not, and you combine all of them to give a general output that then you use to classify your event into signal or background, okay? In order to determine the optimal values of these WYs here, what you can do is try to minimize the prediction, the real prediction of this, or the real label of the event, compared to this value that is given by the classifier, okay, by the strong classifier, and then you minimize this according to these values WY, and you select the best possibilities, okay, for these values, and then you have your strong classifier. If you expand this expression and you introduce a lambda parameter, which is a regularization parameter that you see here that only affects the WY, okay, so if, what we are doing here is penalizing the inclusion of many weak classifiers in the strong classifier, okay, so this lambda is greater than 0, so if I add, for instance, all the WYs, this value is going to increase, so this favors that many of these values WY are 0. So if you expand this and include this term, you obtain this expression here with these coefficients. It's easy to check, it's just algebra. And you see here that this is equivalent to an Ising model. Okay, so now we have something that we want to, or in fact, a cubo formulation of an Ising model. Okay, so this is something that we can use with these quantum annealing computers. Okay, with these D-wave quantum computers, and this is exactly what the researchers did. And here I'm showing just one of the figures in the paper. You can check the paper and see other results. But this is interesting to me because this is a kind of behavior that we are going to see next week also when we study quantum machine learning, different quantum machine learning algorithms, okay? So here we have in green the quantum annealing result. This is the area under the receiver operator characteristic curve. I'm not going to explain in detail what this is, but the higher this value, the better is the classification, okay? So you see here that for quantum annealing and simulated annealing, that is a method that we are also going to use and explain in a minute. You obtain these results here that with a number of events in the training data set that is small, outperforms the result obtained with, for instance, deep neural networks or this other classifier, which is an ensemble of decision trees, okay? Then when you increase the number of events in your data set, these classical algorithms outperform the quantum annealing method. But to me, it's interesting that at least for a small training data set, you can obtain some advantage by using this quantum method. And this is something that we are going to see also in other algorithms, okay? So this is an application in high energy physics. There are several others, but now I want to, if there are no questions, okay, I want to go back to this slide where I have a couple of links that are also included in the Indico page for the lecture. That we are going to use to try these quantum annealers from D-wave in a simple problem. Okay, so similar to what IBM does with these quantum computers on the IBM Quantum Experience, D-wave, which is a Canadian quantum computing company, is doing with a platform that is called LEAP. In the case of LEAP, you don't have completely free access as much as you want, as in the case of the IBM Quantum Experience. You have a limited number of resources that you can use. It's, I guess, 1 minute per month, okay? But at least it's something that you can use to try some of these quantum computers and run some algorithms. Okay, So in order to use this, you can register for free following this link. I have already a browser with this page. Okay, so I'm going to move there, and you need to sign up. Okay, it's free. You need to provide an email address and some information, and then you can use this system. Okay, so I'm going to log in. I already have my account created. So while you create your account, let me okay, problem with the password. Okay, now I'm in. Okay, so once that you sign up, you are going to see this screen, this dashboard, in which you have some information about the different quantum computers, quantum annealers that you can use. Okay, recently they have included these hybrid solvers, which take the problem that you want to solve and decide whether to run some part on a classical computer, some part on a quantum computer. I'm not going to focus on them, because I think the interesting part is to focus on these two quantum annealers that we can use directly. Okay. Initially, when the system was launched, the platform was launched, we only had access to these DW2000Q systems, which implement, as you can see here, if you click on the information, they implement more than 2,000 qubits. Okay, and this may seem surprising, because on the IBM quantum computer we are using devices with 5 or maybe even one that is 16, and here we have 2,000. Okay, so why this difference? Well, the difference is because, as we mentioned in the slide, these computers do not implement any possible Hamiltonian. They only implement Ising type Hamiltonians. Okay, so they have more qubits, but the operations that you can do on them is much more restricted. You cannot do any possible quantum circuit or any possible quantum evolution that you would want to do. Okay, you can only solve this kind of problem, and because they only implement this kind of evolution, it is much easier to construct one of these devices. It's not easy anyway, but it's easier than to do this with 2,000 qubits with all the possible gates that we have been studying. Okay, so you have this this computer with 2,000 qubits, and this new one, which was added only a few months ago, if I remember correctly, this has even more qubits. This has more than 5,400. Okay, so here you also see the percentage of the subscription that you have used so far. In your case, it will be 0. Okay, and here you have information which is similar to the one on the IBM quantum computer, IBM Quantum Experience. You have this token that you can use to install locally the development tools that allows you to use these systems remotely with a Jupyter notebook or with a Python script. And I have included in the on the Indico page for the lecture a link with instructions for installing locally these libraries and to use this token and to run your programs remotely from your own computer. Okay, you also have here information about the plan that you are enrolled in. You have this free plan that you obtain when you register for the first time, which gives you 1 minute per month the first month, and then you don't have any more resources. but you can get more time by either paying for a subscription or registering as a developer. Okay, so if you have a GitHub account in which you regularly publish your code, you can just use that GitHub account, register as a developer, and then you obtain 1 minute per month. When you run out of time, you only have to wait until the next 30 days period, and then you get another minute in order to run your algorithms. Okay, so you can use this system, you can register for free, you can use it remotely, but recently they also added the possibility of running your programs also on a platform on the quantum computer or on the cloud, okay, without needing to install anything. So in order to do that, it's a little bit more complicated than in the case of IBM's quantum experience. What you need to do is to first publish your script, your Python script in GitHub, for instance, and then you access this GitHub script from the cloud platform. Okay, I have prepared one of these scripts, and I have gave you here the link to be able to run this without installing anything. So once that you register, you sign up for the account, if you click here, you will see something like this. A new workspace will open for you, and this links to in this case my Python script, which is also published or uploaded to the Indico page, and it's also published on my GitHub account. Okay, and then it loads a new workspace, and you will be able to see the Python code. Okay, I don't know if it is big enough. I'm going to do it a little bit bigger. Okay, so here I'm importing NumPy, well, just to use some functions from NumPy for combinatorial optimization. And then I need to import this module, which is the one that implements the different methods that we are going to use in order to solve one of these optimization problems over an Ising model. Okay, using this is very simple because this is completely transparent to the user. You only need to provide the coefficients of the Ising instance that you want to solve, for which you want to obtain a ground state, and then you can use the different minimizers provided by D-Wave. Okay, so in order to specify the coefficients of the Ising model, we can use this dictionary in Python, which states that, for instance, in this case, I have two elements, two particles, and the coefficient for the term of the interaction between these two particles is 1, and I don't have any bias, any coefficient affecting only one of the particles. Okay, so this is a very simple example of the max cut problem, in which we have a graph with two vertices, 0 and 1, which are connected. Okay, so this is very simple, only to show you how this works. Okay, and then what I'm going to do is to create a model specifying the coefficients h, the coefficients j. This is another value that it's added to the energy value in order to obtain a displacement of the energy. This is not very important. Okay, and then you specify whether you want to solve this in the Cubo model or in the Eisen model. If you want to use the Eisen model, which is our case, you specify this to be spin, okay? And then, well, let me run this. In order to run this, you have to click on this green triangle here, okay? And then you will open a terminal in the bottom of the, it will open a terminal on the bottom, and everything is going to be executed. So let me show you the code. This is executing on the background and show you the different results. So I have declared the Ising model that I want to solve. Okay, so here I'm printing the information. This is the Ising model that I'm going to solve. Notice that it has included coefficient 0 for the H term that I had left empty. And then I'm going to solve it first exactly. Okay, I'm going just to compute all the different possible solutions and the energy that they give. Okay, so here we have that this is the output of this call here. So we have that for the solution -1, +1 -1, and for the solution -1 +1, which corresponds to assigning different groups to each of the vertices in the graph, we have energy, of course, -1. Okay, and for the other two solutions, we have energy 1. Okay, so the minimum energy is obtained with either of these solutions. Now we are going to use also for comparison simulated annealing. Simulated annealing is this other method that was used in the paper that I showed you before, in which they compared the quantum annealing to other methods. So this simulated annealing, maybe some of you have used this heuristic optimization method in the past, is a classical algorithm in which you start with a random solution, in this case an assignment of 1s and -1s, and then you randomly select one of the positions, and then you flip the value. If you have a 1, you change it to -1. If you have a -1, you change it to 1, okay? And then you compute the new energy of this state. If the energy is less than what you had before, then you accept this change and you repeat. If the energy is higher than the energy that you had before, then you could accept this change with a probability that decays exponentially depending on the time that you have been running the algorithm. So at the beginning, you have a high probability of accepting changes even if they increase the energy of the state. But once that you are running the algorithm and you have run several different steps, the probability of accepting solutions which worse energy decreases exponentially. Okay, so this is apparently inspired by physical processes of cooling of materials, in which at the beginning, because of the temperature of the material, you have more freedom for the particles to move, and then once that the material reaches lower energies, lower temperatures, it is more difficult for the particles to move. Okay, so this is a method that can be used in several different optimization problems, and we are using it here, and we are sampling, we are repeating this several different times, and we are sampling in this case 10 times to see what we obtain. And well, since this is a very, very easy problem, in the time runs of this simulated annealing, we have obtained the minimum energy, sometimes with the +1 -1 solution, and one time here with a -1 +1. Okay, very easy problem, and this method gives you the solution with no problem. Okay, now we are going to use the quantum annealer, the actual quantum device. For that, we need to import these objects from the wave, and then we construct with this instruction, with this order, we construct a sampler, which is what we are going to use to access the computer and retrieve some approximations of the solution of our problem. Okay, this instruction here is just to retrieve the name of the computer. Remember that we had two different devices, the one with 2,000 qubits, the one with more than 5,000 qubits. By default, you see here that the one that we, oh, okay, so in this case, maybe I change it from the other, when I run it first, I change it, and as by default, it is using the last one I was running in. Okay, well, if I want to change, I'm going to change it here for you. So if I want to change to the other computer, I need to use the name that is the description of this computer. I'm going to copy it here, and I need to use the order like I'm using here with solver. Okay, so let me go back. Oh, where is it? Sorry. Ah, here. Okay, so solver is this one now. So I'm going to repeat this. Okay, and then now I'm running on this solver, and I'm retrieving the solution. Let me see where this is. Okay, this is the new execution. So I'm retrieving the solution with this solver, the one with 2,000 qubits, and I have run this for 5,000 times, and more or less half of the time it has obtained the solution -1 + 1, half of the time it has more or less obtained the other solution. Okay, so this is expected because this is a very simple problem. Okay, I just wanted to show you how to use this kind of computer. Now let's use some little bit more complicated example. Here we have another instance of the max-cut problem because all the coefficients are set to 1. You can change this to run a different Ising model, okay? But this is easy to interpret, so that's why I'm keeping these max-cut examples. And here we have 5 vertices in the graph, and each one is connected to the next one, forming a circle, okay? So here I'm not going to be able, as in the previous case, to form a cut that cuts all the possible edges in the graph, because since they are connected in a loop and the number of vertices is odd, 2 of them are going to be in the same group. Okay, so the minimum energy that I'm going to obtain with this is not going to be -5, which is the number of edges that we have in the graph, because it's impossible to cut all of them. Okay, so now we are going to do exactly what we did in the other case. We are running to run the algorithm that exactly solves all the different finds all the different solutions and computes their energy. Okay, so now we have 5 different variables, so we are going to have 32 different solutions, and you have here all the 32 different solutions, and the ones with minimum energy are these ones here. Okay, they are again paired 2 by 2, because if I have an assignment that it's 0 to this vertex, 1 to this vertex, that is the same as changing the assignments of vertices. Okay, so in this case we have 2 different solutions that give rise to 4 different possibilities by changing this white and black one with the other. Okay, so these are the possible solutions. We are aiming to find an energy of -4 also with the simulated annealing, and we obtain it for the 10 different executions. And again, we execute with the quantum annealer, in this case with the one that has 5,000 qubits, and you see here that most of the time it has obtained the correct solution, but 3 out of the 5,000 executions that we did obtain a solution which is not optimal. Okay, so this is something that we can find. This is something that can happen. As I mentioned, there is no mathematical proof, and we do not expect to have a mathematical proof that this is optimal, that you can always obtain something that is optimal. Okay, but this is a new method, something that you can use in addition to other methods, classical methods, heuristic methods, artificial intelligence methods that you may use in order to solve this kind of problem. So I think that's all for today. I don't know, let me go back to my screen, see if there is something in the chat. There doesn't seem to be any question, so oh yes, Richard Polivka, and I hope I'm pronouncing that right, has a question, so please go ahead, or you can turn on your mic and ask the question. Yeah, okay, so yeah, the question is, I have read that the quantum annealers are using the tunneling effect. So can you elaborate on that, please? Well, this is somehow controversial. Maybe we can discuss this in more detail next week. But the idea here is that there are some studies that show that when you have different solutions that are separated by a high but narrow potential, okay? So this is something that in a classical algorithm you could not climb in order to obtain a different solution. There has been some evidence, some practical evidence in some experiments that for some of these problems with this kind of potentials or this kind of landscape in the energy, in the landscape energies, the quantum annealing technique, it's able to jump from one of these solutions to the other. Okay, so this is something that in principle you could not do with a classical system, and it is supposedly because this quantum tunneling effect. Okay, because you know that in quantum mechanics, this is an effect that you can have, that a particle can jump at this barrier, this potential barrier, although physically in a classical setting this should be impossible. Okay, but there is some discussion about this. It is not clear that this is the case. There has been a lot of controversy on all that is related to the performance of these quantum annealers. As soon as somebody publishes a result that these kind of techniques work for certain problems, other people do a different research and show that for different instances of the same kind of problem, then the quantum annealer does not work so well. So it's not clear. It's not clear if this is exactly what is happening. I can show you, or I can search for more information or more detailed resources for you to take a look into this. But to me, it's not clear that this is what is happening. Okay, because it does not happen all the time. It only happens for selected situations or selected problems. Okay, any other question? Well, so thank you very much again for your attention. We'll meet again next week, and hopefully you will be able to watch the recording both on the CERN document server and on YouTube in the next few days. See you. Bye.